In this second part of our virtual lecture for today, we are going to focus on something called an empirical formula. Now, empirical formulas have a number of different applications and uses for them, but most importantly, what they tell us is kind of the simplest way of expressing how many atoms of one kind there are relative to other elements in a compound. And so to start this discussion, we need to look at chemical formulas again. And so when we talk about chemical formulas, or at least when we've talked about them up until today, everything that we've talked about has focused on molecular formulas. That is the actual number of atoms of one element compared to other elements in a compound. So for example, carbon dioxide. Carbon dioxide has a molecular formula of CO2. There is one carbon for every two oxygens in one molecule of carbon dioxide. Now in compounds, especially ionic compounds, the word molecule doesn't get thrown out nearly as much because it's not really an accurate representation of what that ionic compound looks like. And so formula unit tends to be used more often, but the principle is the same. A formula unit tells us the ratio of one element or one ion to another in a compound. So for example, magnesium chloride. Magnesium chloride exists with a 1:2 ratio of magnesium ions to chloride ions in that substance. Now, molecular formulas give us the exact number of atoms in a given substance. Empirical formulas simplify that process a little bit, and they do so by expressing our ratio of elements not in terms of what they actually are, but in terms of a mathematically simplified version. In short, empirical formulas are the simplest whole number ratio of one atom to another in a compound. And they're always written with whole number subscripts, 1, 2, 3, 4, 5, and so on. This is different from the molecular formula because molecular formulas don't necessarily care what the simple ratio is. They want you to know how many atoms of each kind are in the compound itself. Now, sometimes empirical formulas and molecular formulas are the same. Carbon dioxide, magnesium chloride are two prime examples. The empirical formula, carbon in a 1:2 ratio with oxygen, is the same as its molecular formula, CO2. Magnesium in a 1:2 ratio with chloride ion is the same as its ionic formula, MgCl2. But there are some cases where they are not the same. And in particular, in certain types of substances known as organic materials, it is especially this way. So let's investigate them a little bit further. As we've mentioned before, we're talking about the smallest whole number ratio of one element to another in a compound. So let's look at these two compounds and see if we can determine what that simple ratio would be. On one hand, I have C6H6. On another hand, I have C2H2. Now, what's interesting in both of these cases is that the numbers can reduce in both cases. Both of these numbers in C6H6 are divisible by 6. And so if I divide them by 6, I get the simple whole number ratio of 1:1. And that makes my empirical formula CH. Now in the second example, C2H2, both of those numbers are divisible by 2. So if I divide each subscript by 2, I get the same empirical formula of CH. So in both cases, CH is the empirical formula for those compounds. Now, just because two compounds have the same empirical formula does not mean that they are the same molecule at all. In fact, acetylene and benzene, these two substances depicted here, are very different from each other in a number of different ways. Benzene is a liquid, acetylene is a gas, Both are flammable, but in very, very different ways. There's lots of things that are different among them in terms of their bonding and their properties. All that the empirical formula does is it says that they do have something in common. If we break it down to the purely atomic level, there are the same number of carbons and hydrogens in both, at least in terms of their ratio to one another, their relationship to one another. But what about these two compounds? H2O2 and H2O. Are they different? Are they the same? Well, again, for H2O2, I can see that I can divide both of those numbers by 2, and that would give me the empirical formula of HO, or OH. But for H2O, there's no number I can divide those two things by that would give me whole numbers at the end. Oxygen is already at 1. To divide it further would turn it into any kind of a fraction, which would not be a whole number. So its empirical formula is H2O. So here I have an example of two different compounds with two different empirical formulas. And that's okay. That just tells me that the relationship of one atom to another in those two compounds are different. Let's take a look at another example. What is the empirical formula for copper 2 oxide? Copper 2 oxide, I can look at this and pinpoint, okay, let's use a couple of different colors here. I can see that there are 1, 2, 3, 4, 5, 6 copper ions, and there are 1, 2, 3, 4, 5, 6 oxygen ions. 6 copper, 6 oxygen. My empirical formula would be CuO. Now, from your nomenclature unit last week, you should be able to understand that the molecular formula is also CuO for copper 2 oxide. In this case, the empirical formula and the molecular formula are exactly the same. And again, that's okay. All we're doing is pinpointing the ratio between them. So when it comes to identifying empirical and molecular formulas, the real question that you have to ask yourself is this: does the formula that I'm given reduce? Think about the concept of reducing fractions that you learned in algebra. If I can take both of those numbers, both of those subscripts, and divide them by a common factor and get whole numbers at the end, then what I'm dealing with is a molecular formula that is not an empirical formula. And so if I can look at cyclopentane here, cyclopentane, C5H10, I can see that each of these numbers are divisible by 5 to give me an empirical formula of CH2. Cyclohexane, I can see each of these numbers can be divided by 6 and give me an empirical formula of CH2. Ethylene, I can see that both of those numbers can be divided by 2. I get an empirical formula of CH2. H2S, no number I can divide by other than 1. In that case, the molecular formula and the empirical formula must be exactly the same. For ionic compounds, again, there is no molecular formula for them because they exist in these wide arrays, these crystalline structures. So we really don't have a good telling on how many atoms there are in the structure itself, and that's okay. But we do know that the empirical formula is the ratio of one ion to the other. Let's do some other practice. Practice problem is this. Determine the empirical formulas for these substances. For which substances is the empirical formula the same as the molecular formula? Now, the key to this problem is understanding what my formula is, and therefore, can I reduce it? So, I look at HGO. HGO exists in a 1-to-1 ratio already. I can't reduce it further. It's going to be the same as empirical or molecular. In CH2Cl2 up here, I've got 1 carbon, 2 hydrogens, and 2 chlorines. Well, since I only have 1 carbon, I can't reduce it any further. This is the empirical formula and the molecular formula at the same time. Both are there and present at the same time. This one, C6H3Cl3, I can divide each of those by 3 and get C2HCl. That is the empirical formula, which is different than the molecular formula. Oxalic acids, H2C2O4. Each of those numbers is divisible by 2. The actual empirical formula is HCO2. N2O4. Each of those numbers is divisible by 2. NO2 is the empirical formula for that substance. P4O6 down here. Each of these numbers is divisible by 2. I get P2O3 as my empirical formula. N2H4. Each of those numbers is divisible by 2. I get NH2 as my empirical formula. C2H6. Each of those numbers is divisible by 2. I get CH3 as my empirical formula. Now, I've saved these 2 other ones for last because they're the most complicated. To figure out whether or not I need to reduce these, I have to get them all kind of combined again. So CH3CO2H, I can see I have 2 carbons, 3 plus 1 is 4 hydrogens, and 2 oxygens. Seeing it now written like this, I can see that each of those is divisible by 2. CH2O is my empirical formula. This one here, the one on the bottom, CH2CHCH3, I can see that I have 3 carbons and 6 hydrogens. Each of those numbers is divisible by 3. My empirical formula is actually CH2. So all told, there were only 2 on this page that actually had the same empirical and molecular formulas. And one of them, mercuric oxide, really doesn't count because it's an ionic compound in the first place. So CH2Cl2 is really the only one that behaves that way. Everything else on this page, and that, again, this is the case for most organics, so a lot of these carbon-containing compounds have this kind of empirical property to them. One last concept to go over here, and it's the idea of a molecular formula as a function of the empirical formula. We talked in our previous class about molar mass, the idea of I can take the formula of something, add together its components on the periodic table, and come up with a molar mass for it, simply by adding together the elements that make it up. Now, from an empirical formula standpoint, I can understand that an empirical formula is part of a molecular formula. And so if I can take that same idea for the empirical formula, take its elements, add together their masses off of the periodic table, and put it on together, what I can find is the empirical formula mass. And I can compare that empirical formula mass to the molar mass of the substance to figure out how many times bigger the the molecular formula is. And so if I do that, I can do a direct comparison and see for myself, okay, if I have an empirical formula of CH2, and the real thing is actually C3H6, then this one chunk represents 1/3 of the mass. And so if I knew the mass of this chunk, I can multiply it by 3 to get the mass of the whole substance. So let's put that into action. We've determined that an empirical formula of a substance is CH2. The molar mass is determined to be 42.12 grams per mole. What is the molecular formula for the compound? Well, the first step, we are told that we have CH2. So to find its molar mass, I need the mass of carbon plus the mass of 2 hydrogens to find the empirical mass. Molar mass of carbon, 12.01 grams per mole. Molar mass of hydrogen, 1.01 grams per mole. And so if I put those two together, I get 14.03 grams per mole as my empirical mass. Now I compare these two masses to each other. How do I do that? By division. 42.12 grams per mole divided by 14.03 grams per mole. If I do the numbers, 42.12 divided by 14.03, I get 3. And so my molecular formula is equal to 3 times my empirical formula, which is 3 times CH2. So I'm going to distribute that 3 over both of those subscripts. I end up with C3H6. Okay, last problem on this particular video. What I would suggest you do, go ahead and pause this video, try to determine the empirical formulas, come back in a few seconds. After you're done, hit play again, and we'll go through the answers one by one. So go ahead and hit pause right now. Okay, so we've been asked to determine the empirical formula for these compounds. Again, all that we're really looking for is there a number that I can divide both of the subscripts by to give me a lower reduced form of the ratio between the two elements, or the three elements in some cases. Now, for CH4, I have 1 carbon and 4 hydrogens. I can't reduce a 1 any more than it already is. So if I have a 1 in my formula, I automatically know its empirical formula and molecular formula are the same. So CH4, I had 1 carbon and 4 hydrogens. The empirical formula is also CH4. Same thing with the ammonia on the bottom. 1 nitrogen to 3 hydrogens, I can't reduce that fraction anymore. NH3 is the answer there. For the rest of these, I have to at least evaluate if there is a number that I can divide them by. So in the case of C3H9, sure enough, I can divide each of those by 3, and if I do, I get CH3 as a result. Each of these numbers in glucose, C6H12O6, I can divide by 6. I end up with CH2O as a result. P4O10, I can divide each of those numbers by 2, and I end up with P2O5 as a result. Last one here, S2O6, I can also divide that one by 2. I get SO3 as a result. So this is as far as we are going to go for empirical and molecular formulas in this course. There are other sections in this book that go further than this, but we are going no further than right here. And so your assignment for today is to complete the post-lecture for section 4.2 and to use this data, this information from these 2 videos today to take you that direction and to go where you need to go. If you have questions, feel free to email or send me a message, but otherwise I will see you at our next lecture. Have a good day.